All right, it's 10:45, so let's begin. I don't know if the mic will stay for long, but we can try. It seems that the batteries are dead and there are no new batteries. All right, so we are discussing pressure-driven flows. We want to have a pressure difference driving the flow, so the plates are at rest. And what we want to focus on really is trying to calculate the velocity profile. But some assumptions before we move on further. So some assumptions are steady. Assumptions are steady, no gravity, very similar to last time, no gravity, unidirectional, so same idea, the flow is only happening directional, so small v is equal to 0, no y component, so steady, no gravity, unidirectional. I believe I am not missing anything else. And we cannot say pressure is constant, right? Because we are applying a pressure difference, so pressure is not constant now. Okay, so steady, no gravity, and unidirectional flow. And if I remember any other assumptions we make along the way, we can do that. But the usual ones also apply: constant mu, constant rho. That's standard for using the equations to begin. Okay, so don't forget the constant mu, constant rho. All right. So we have three variables again: u small u of xyt, small u of xyt, small v of xyt, and pressure of xyt. All right, I can say it's steady, so there is no time dependence. This is equal to 0, so this just completely goes away. So this implies that u is a function of x comma y and p is a function of x comma y. Okay, u is a function of x comma y and p is a function of x comma y. Any questions here first? Okay, so very similar to last time. The only difference is last time we had also said that the pressure is also constant, but now because pressure difference is driving the flow, we cannot say pressure difference is constant, so we can say p is a function of x and y and u is a function of x and y. Okay, all good? All right, so let's keep going. Continuity equation first. Continuity equation. So very similar process as you are seeing again and again. Sorry about that. Same process. Del u by del x plus del small v by del y is equal to 0. This is exactly 0 because small v is 0. So I get del u by del x is 0, same as last time. Okay, what does it imply? Del u by del x is 0. U is only a function of y, right? Because it doesn't depend on x. So this further implies that I can drop this. So I can say u is only a function of y. Perfect, right? So u is only a function of y. By the way, I just want to make a note here. In some classes in undergrad fluid mechanics, they explain this in more detail, and we'll talk about this in more detail in the third part of the course a bit more. This sometimes is called fully developed assumption. And what happens is some books will say assume fully developed and then we'll show that the small v is 0. We have said small v is 0, so we get del u by del x is equal to 0. But some books will say, oh, del u by del x is 0 because it's a fully developed assumption, and then we'll say small v is 0. So I just want to make this, I want to clarify this. If you read the book, it may talk about fully developed, but you don't have to worry about it too much. Okay, so it's alternatively sometimes said alternatively. So I should want to clarify this is alternatively called fully developed. Okay, assumption. That means that the velocity itself does not depend on its own coordinate. It's an x direction velocity, but it doesn't depend on x. So that's what it's called fully developed assumption. Okay, and we'll talk about this in a bit more detail in third part. But for now, for this purpose, don't have to worry about it too much. All right. So small v is equal to 0. U is a function of y. Now we go to Navier-Stokes equation again in both x and y. So let's do Navier-Stokes equation. I think I'll write here just in case, just for clarity, Navier-Stokes equation. So we have rho of del u by del t plus u del u by del x plus small v del u by del y is equal to minus del p by del x plus mu del square v del square u by del y square, so del x square del square u by del y square plus rho gx. Okay. Similarly, I have p rho del v by del t plus u del v by del x plus v del v by del y to minus del p by del y rho del square v by del x square del square v by del y square plus rho gy. Okay. Right, so I've just written down the equations. What I have not done is I have not included the z component because it's a two-dimensional flow and we are just focusing on x and y dimensions. Okay. So much like the last time, we'll start to cross off terms one by one. Again, very similar to shear flows, just a slightly different setup. So what happens to del u by del t? 0 because steady, right? What happens to u del u by del x? 0 y, continuity equation, or u does not depend on x, right? Plus 0 from continuity. This is 0 because v is equal to 0, right? So the left hand side completely goes to 0. Is minus del p by del x 0? No. Why? Because we are applying the pressure gradient, right? So we cannot say, it may come out to be 0, but we cannot say it is 0, right? We are applying a pressure gradient. So that is there. Then what happens to mu del square u by del x square? 0 because del u by del x is equal to 0. Del square u by del y square stays because u is a function of y. So this stays, and then rho gx is equal to 0. Okay, because there is no gravity. Okay. Any questions on the simplification here? So it's identical. The only difference is now we have not dropped the pressure gradient term. Okay, it's identical. The only difference is we have not dropped the pressure gradient. Let's keep going for the y direction. So this is the x direction. So recall in the y direction, there was the question somebody had asked last time, why, I think about the y direction component of the system. We showed it was 0 equal to 0, but let's do what it teaches us in this time, okay? Small v is equal to 0, so this goes away. Small v is equal to 0, small v is equal to 0. So all of these are 0. Can I drop del p by del y? No, we don't know, right? It's a pressure, we are applying a pressure gradient, so we can keep it. This is equal to 0, this is equal to 0 because small v is equal to 0, no gravity. So this again goes to 0. Okay? So all of this gives us two equations. The x momentum equation tells us del p by del x is equal to mu del square u by del y square, and the y momentum equation tells us del p by del y is equal to 0 because the rest of the terms are 0, right? There is nothing else which stays. So these are the two equations we get. Del p by del y is 0 and del p by del x is equal to mu del square u by del y square. Okay. Any questions here? I know we are doing it a little faster than last time, so I want to take a moment. Any questions on any of the terms? Anything which is confusing? All good? Okay. So recall I had said we had already said u is a function of y, p is a function of x and y. Right? What does this equation tell me? Del p by del y equal to 0. What does this mean? P is only a function of x, right? Because del p by del y is 0. So I can drop this and we can say u is a function of y and p is a function of x. Does everybody agree with this? Okay, p is only a function of x, u is only a function of y. This is what the y momentum equation tells us. Now we go back to this equation here. I hope you will all allow me to do this. It's not del p by del x, it's actually, and not del square u by del y, it's actually dp by dx, because p only depends on x, it does not depend on any other variable. And this is mu d square u by dy square, because u only depends on y. This is the final equation that we have basically found. And this also agrees with what we got last time. When I did not apply pressure gradient, I had gotten mu d square u by dy square is equal to 0, because there was no pressure gradient, right? So same equation as last time, but now I have a pressure gradient or dp by dx. All right. Now how do I integrate? This has two variables, x, there is a variable y on the right hand side. How can I integrate this equation? I have to integrate it, and obviously I need to apply boundary conditions, but any thoughts on how can I integrate this? Yes, go ahead. Yeah. So correct. So dp dy equal to 0 already implies pressure is a function of x. So that information we have used. So good suggestion. That information we have already used though. So dp by dx is equal to mu. So do you think the left hand side is a function of? Yeah. Go ahead. Yes. So yeah, I'll come to that in a second. So boundary conditions we definitely need. I will come to that in a second. Yes, go ahead. Mm-hmm. Yeah, very good. Almost there. So perfect. So what the suggestion is that we know the left hand side is only a function of x, right? And the right hand side is only a function of y. So how can a function of x always equal to a function of y? When they are both constants, right? So left hand side is simply a constant number. dp by dx is not varying. It is just simply a constant number. dp by pressure is changing, but dp by dx is constant. Okay? Because yeah, do you have a question? No? Okay, all right. So dp by dx, so they are both constant. This is a function of x. Function of x, and this is a function of y, and I cannot have a function of x equal to a function of y unless they are both constants, which implies that dp by dx is simply constant, right? Or I can write this as delta p by L. So what does it mean? dp by dx is constant, just simply changing from p1 to p2 linearly, right? So I just go from P1 to P2, sorry, I can have, let's say, the opposite one for now. P1 to P2, I simply change it linearly in terms of x, because dp by dx is constant. When a derivative is constant, the function is linear. Or I can say dp by dx is simply delta p by L. Okay, make sense? Any questions here? Yes, go ahead.
Can you re-explain why, because it's a function of x equals a function of y or constant?
Yeah, so imagine like this. If left hand side was x square and this was y square, I cannot have them equal to each other. They have to be numbers. Like if they are functions of x and y, I cannot write them to be equal to each other. Make sense? Another way to think about it is you can, if I differentiate something with respect to x, left hand side, the right hand side will go to 0. So you can get d square p by dx square is equal to 0. So basically, the different ways to mathematically show it. But the simplest way I think about it is, this is a function of x, this is a function of y. They cannot be always equal unless they are both constants. And if they are constants, we know that dp by p changes from p1 to p2, so it has to be same as delta p by L, the left hand side. Right? Any questions here? Do ask questions if there is any confusion, by the way. It's very important to discuss all these things, okay? So this means that we go from basically mu d square u by dy square is equal to delta p by L, okay? All right, mu d square by dy square is equal to delta p by L. And now what I need, and right hand side is constant. Delta P by L is just a number, right? I can now integrate in Y. So I need two boundary conditions because I have a second order equation in Y. So I need two boundary conditions. And what are the boundary conditions? I have a plate here. I'm trying to flow through the system, P1, P2. So what should I expect the velocity boundaries to be? Yes, so there are two values, y equal to minus h and y equal to plus h, exactly. There are two plates which are my boundaries, y equal to minus h and y equal to plus h. And what is the boundary condition at both of them? Both the plates are at rest. So the velocity in the x direction should be 0, right? No slip boundary condition. So u of 0, the u of minus h is equal to 0. And u of plus h is equal to 0. These are my boundary conditions. And both are no slip, okay? Any questions on the governing equation and boundary conditions? Anything that's confusing or want clarification? Let's take a moment to see this equation. Any questions? So does anybody want to suggest any other boundary conditions? So these two boundary conditions are perfectly valid. I use them personally. I prefer to write like this, but some students are more sort of want a more intuitive, sometimes boundary condition, and that is a plane of symmetry, right? There is no difference between the top plate and the bottom plate. So I can also say that the velocity should be symmetric about x is equal to 0. It should look the same. If I'm looking up from x is equal to 0, x is equal to y equal to 0, so from the center of the line, symmetry about y equal to 0, then it should be the same, like it should look the same. So that is called del u by del y at y equal to 0 is equal to 0. This is an alternate boundary condition, one of them. Alternate boundary condition, symmetry, okay? Symmetry, okay? If this is not true, and this will automatically, you can use, so by the way, I should note, if I have 1, 2 and 3, so let's label them. If this boundary condition is 1, if this is 2, this is 3, you can use any 2. You can use any 2 you want and it will give you the same answer. It has to give you the same answer. Otherwise the physical setup is wrong. I will use 1 and 2 because that's what I prefer. I find them to be intuitive. But you can use 1 and 3 and you will get the same answer. It shouldn't matter. Okay, I just want to clarify that. Any other questions here? All right, so we'll integrate in y, and I will do this a little faster. Integrate in y. Integrate in y. Okay, so mu d square u by dy square times dy is delta p by L dy. Okay, so this becomes mu du by dy is equal to delta p y by L, or maybe easier to just write as mu here plus c1. Maybe let me just write this as delta p by mu L dy. Okay, I have just taken the mu here. I have taken the mu on the right hand side plus c1, and then I will do another one which will be u du by dy is equal to delta p y by mu L plus c1 dy, and this will give you u is equal to delta p y square by 2 mu L plus c1y plus c2. Don't worry, I know this is a little bit of math pretty fast. You can do this, if you are not as used to some of the integrals, you can do this very easily yourself, and you will be able to get to this point, delta p by y squared by 2 mu L plus c1y plus c2, and then you apply boundary conditions to find c1 and c2. Apply boundary conditions to find C1 and C2. Okay. I will not do this. I'll just directly give the answer. You will do this in your homework problem and exam practice problems, and you will get practice. It's just math, like plugging in and just being careful of the signs. So what you do get out is this U is equal to minus delta P by L, small h square by 2 mu, h square by 2 mu. Just want to write h clearly, h square by 2 mu into 1 minus y by h whole square, and this is the final equation for u as a function of y. Okay, this is what you get for doing finding the full velocity profile. So instead of a linear velocity profile, now we have a parabolic or a quadratic velocity profile instead of a linear velocity profile. So in the shear flow we got a linear velocity profile, but now I have a y square dependence to get the velocity profile. So that's the key difference here. Some notes: if delta P is 0, I don't get any velocity, which makes sense. If I'm not applying a pressure difference, I will not get a velocity. There is a comment here about delta P being negative, which is correct. Only if my delta P is negative, I get a positive velocity profile, which is what I see here. That's why there is a negative sign in the initial value. And if my viscosity if I want to have the same velocity, then and if I increase the viscosity, then I need to have a higher pressure drop, right? So delta B, like viscosity in the denominator, or you can think of if I'm applying the same pressure drop, and if I have glycerol versus water, glycerol will move more slowly because it's inversely proportional to mu. So now my velocity profile is actually dependent on mu. It is not unlike the system which we saw in this case, because we are applying a pressure drop and we are not just moving a plate. Okay. Any questions here in the process? Okay, I'll recap the process, but any questions here? Anything that's confusing? Yes, please.
Looks like on the last problem you went from 0 to h, but on this one you went from negative to h.
Correct.
Would stuff cancel out if they set this up the same way as we did?
Absolutely. So good question. So what if I had set this up from 0 to h, right? By the way, sorry for the small error here. I believe I had a small h, right? I made a capital H in this figure. Let me just correct this one. This is y equal to small h. Apologies, I just completely mixed up two notations. So y is equal to h minus h, and even here minus h and small h. Please make sure you're not confused. Apologies for that. I think this is all should be fine. Okay, thanks. Yeah. So to answer your question, yes, if you go from 0 to h, you will have to get the same answer, but note that now my coordinate system has changed. So let me put it this way: if I was to plot two different velocity profiles and use one coordinate system and second coordinate system and overlay them, they will match, but the expression will not look identical because now my y is shifted, right? My y is shifted, my h may have a different definition. So that's really a good question, perhaps a good supplementary video, for instance, like this, where you change the coordinate system, I can actually show how they're both identical and have to come out to be the same. So that's a very good question. It will come out to be the same. It has to. Yeah. So you get this velocity profile. Any questions on the other in the calculation? Okay, so let's quickly review. Okay, so what we did was we first did the assumptions of steady, no gravity, unidirectional, constant mu and rho. Continuity tells us use a function of y. Navier-Stokes equation gives us two equations: del p by del x is equal to mu del square u by del y square, and del p by del y equal to 0, which means use del p by del y equal to 0 means p is a function of x. So I essentially leave with u is a function of y, p is a function of x, and if I want this equation to hold, then dp by dx is constant, or means the pressure profile is linear, or I get mu d square by dy square is equal to delta p by L. We apply the no slip boundary condition on top and bottom plate, and then we just integrate out and get to this velocity profile. Okay, there is still a little bit of math here. If you are confused, please do try this at home. It's very instructive. Like doing this over and over again, it really helps to see the whole process, and you get this velocity profile. Now let's discuss this velocity profile and some other properties. Okay, so this velocity profile is like this. You get a velocity profile which is now a parabola. Okay, so parabolic velocity profile. Okay. parabolic velocity profile. Can someone suggest where is the velocity maximum? Y equal to 0, perfect, right? When y equal to 0, this term goes to 0, so 1 minus this term goes to 0. So u max, so u equal to 0, so when small u is equal to, at y equal to 0, small u is 0 is equal to u max, and that is equal to minus delta p h square by 2 mu, delta p by l h square by 2 mu is u max. So sometimes you see the velocity being written as small u is equal to u max into 1 minus y by h whole square. Okay, so that's sometimes you see the velocity profile written like this. And by the way, you can put the value of y to be small h or minus h, and then you do get the velocity to be 0, right? So it satisfies our boundary condition. If you put the value to be plus h, then also you get 1 minus 1. If you put minus h, you get 1 minus 1, so velocity does go to 0 in both the cases. So satisfies our boundary conditions. Okay. Now, does anybody remember we had discussed how to calculate flow rate from velocity profile, which is varying function of y? We discussed this in the first lecture after the exam. So to calculate flow rate, what we should do is we do v dot nda, right? Remember that? So in this case, I'll just want to mention that v dot nda, and so you can say outward velocity like this. So this simply becomes u times dy, and I want to clarify if there is a plate length of there is some sort of width w in this height. You can assume like in the z dimension, which we didn't really discuss, going from minus h to h. Okay, so you are calculating, essentially you are trying to calculate flow rate from this entire region. Okay, minus h to h plus h. So I have w into minus h into plus h, u max into 1 minus y by h whole square dy, and I will let you do this yourself, but what you will find essentially when you integrate this is you will get 4 by 3 w, believe that is correct. Think just blanking on a little bit of the calculation. U max times, yes, that is correct. Yeah. So this is what you will get. Okay, right? 4 by 3 times w times h. So I just want to emphasize one thing here, and I'll probably the supplementary. That was a great question about changing the coordinate system, but see, I'm going from minus h to plus h. Okay, from the bottom plate to the top plate. All right, because I'm going from minus h to plus h. If I had a different coordinate system from going from 0 to h, I will just use 0 to h. Okay, in this case we are going from minus h to plus h to calculate the flow rate. Okay, what's the average velocity? Do you remember that? We had discussed this average velocity, u bar, or sometimes you can use u average. I'll just use u average. U average is flow rate by the flow area, by the area, cross-sectional area, okay? Area of cross-section. Does anybody want to suggest what the cross-sectional area is in terms of small h and w? 2h times w, right? So you have 2h height and the width is 2h times w. So we have q by 2h times w. So if you substitute the value, you will get 2 by 3 u max. Finally, what I want to show is that you can also write your velocity profile as u max times 1 minus y by h whole square, or you can write this as 3 by 2 times u average into 1 minus y by h whole square. Okay, this is another way to write this as 3 by 2 u average, So the average velocity is lower than the maximum velocity, is 2/3 of the maximum velocity. Velocity at the ends is 0. And for all the problems that we were doing in part 1, where we were using U1, inlet, outlet, we were essentially treating the velocity to be the average velocity, right? So whenever you have a velocity profile, you can actually calculate the velocity, average velocity, which basically means that if I multiply average velocity by the area, I will just simply get the flow rate, okay? Remember in your part 1, you were doing A1 V1, A1 V is equal to A2 V2. So why were we allowed to do that? Because we were saying velocity times area is flow rate. But now when the velocity changes with respect to y, we can no longer do that because velocity is changing with respect to y. However, if I correctly calculate the average velocity, then average velocity times area is actually equal to the flow rate. So that's why calculating average velocity is beneficial. Yes. So it is 3/2, right? Because u max is equal to, so you're right. So it is u average is equal to 2/3 of u max. So u max is equal to 3/2 of u average. So that's what I'm using. So I'm replacing u max as 3/2 of the u average. Make sense? It's not, have I written something wrong or? Make sense? Okay. Another way, by the way, just to clarify, one thing you can also do is you can calculate u average as 2/3 u max, and that comes out to be minus delta p by L h square by 3 mu instead of 2 mu. Okay? Because u max was minus delta p by L h square by 2 mu. Yeah. Okay. So it's just 3 mu in the denominator. Another way, okay? All right, that's it for today. So this will be enough for you to do your homework problems. And next time we'll just wrap up this on Tuesday, like a little bit of few more details, and then discuss some interesting problems. And then we'll do the review on Tuesday. All right? If there are any questions, feel free to reach out to us. All right, thank you.